Okay. So, hello everyone. Welcome to the second talk in our series on an introduction to topology. Today's talk will be given by R. Vedanta. He's a MMath first year student, and his interests are lie in the region of algebra and combinatorics. He'll be talking about the idea of a topological space and the various ways of constructing topologies and how you can work with those things. Over to you, Vedanta.
Thank you. Hello everyone. We start now with topology and like basic definition and all. I turn off my video now. So what exactly is topology? Topology is basically like some rubber sheet geometry, okay? You have some space and all your things are like a rubber. You can stretch them however you want and all. And think about this thing, like if you're stretching the things and all, definitely distances and angles won't be preserved. That is why we need new terms and new notions. And that is the aim of the talk. I'll introduce some new notions such as connectedness, compactness, and all these things. Those remain invariant. Those are called topological invariant and all. Any two like any two spaces are called homeomorphic if they are like continuous maps. I'll explain in detail. Right now, I'm just giving you guys the idea. So if two spaces are homeomorphic, all these factors which are like topologically invariant, they remain the same. Like if a space is compact and it is homeomorphic to another space, the other space is also compact. Fine. Don't worry if you don't know the definitions and all these things. Mayank introduced some definitions in the previous talk, and today I'll journalize them. Fine. So we'll begin now. X is a set, and this T I'll represent like topology by T and all. T will represent T is basically a subset of the power set of X. It is a collection of subsets and like this elements. These elements in the thing they come from like X is a set, right? So we can make subsets from that thing, and topology is just like a collection of the subsets following some properties. Right now, can everybody follow till now?
Yes.
And so T is basically a subcollection. Oh, sorry, what am I writing? Collection of subsets. So now, what are the this thing? What are the properties that it follows? The whole idea of topology is to generalize metric spaces. Fine. So when you are looking at metric spaces, now I'll write down three properties now. A collection is called a topology only if it kind of satisfies these three properties. The first one is phi and x belong to T. Phi is just the empty set and x is the full space. Second one will be this thing. If you take any arbitrary, if you take arbitrary number of this thing open sets, oh, okay, fine. I haven't defined open right now. If you take arbitrary number of sets and you take the union, that union also has to be in the topology. Are you guys familiar with this thing, the symbols and all? Like this thing means belongs to, and this thing means for all and all.
Yes, yes.
Fine. And this indexing set that can be anything. It need not be this thing. It need not be finite union or something. It can be arbitrary union also. Fine. And the last property is finite intersection of sets is again in the topology. Now, one question which you guys must have right now will be, why is the union arbitrary and the intersection finite? So, it takes some time to think about and all these things. Basic idea of topology was to abstract the notion of metric spaces. Now, in metric spaces, what exactly are this thing? See, now I'll tell you one more thing before this thing. Open sets are this thing, the elements of T. Like any element, any subset of X which belongs to T is called an open set here. Can someone tell me what was open set in metric spaces?
For any point x in an open set,
Hmm.
there is a neighborhood around x which is also in the open set.
Yes, thank you. So now this set minus 1 by 2, 1 by n, both open. This is an open set, right, in metric spaces. Now you take the countable intersection n from 1 to infinity. What do you think will the set be?
Zero singleton.
Yes, zero singleton. So now basically this zero singleton is not an open set. Just this is a basic exercise you can check, like all singletons will be closed only. So countable union is definitely not this thing. Closed and countable union is not there in the topology again. So that is why you take finite in the definition. Find these three properties, like just try to digest all the definitions and all. The process will be smoother if you are this thing. If you have the properties on your fingertips, like phi and x are in T, arbitrary union is there in T, and intersection, finite intersection is there in T. Can I proceed?
Yes.
Some examples of topology. So now, as the whole idea of topology was making metric spaces abstract, we have this thing, like, of course, metric spaces will be an example of topology. So this thing you can fill metric spaces. Second one is a very trivial example. Like you take any set x and t to be phi and x. Fine. Just check like it satisfies all the three properties. Like say phi and x belong to t. Here x is some set, okay, and t is phi and x. So phi and x belongs to t. First property is satisfied. Arbitrary union, like here the only sets are phi and x, so arbitrary union will be x. Like if even if one of the sets is equal to x, the union will be x. If no set is equal to x, the union will be phi. Both are in T. So second property is also satisfied. And the third is finite intersection. Finite intersection, suppose you have like even if one of the sets is phi, so the finite intersection will be phi. And that is the thing, if all the sets are this thing, x, then the finite intersection will be x, which is again in T. Fine. So this is an example of topology. This is called indiscrete topology. It is very important for example. It is very important for examples of properties and all. Please try to this thing. Remember this thing. Third example will be like exactly the opposite of this thing, discrete topology. Everything is open there. Suppose you have a set X, then T will be the power set of X. Like all the sets are there in this topology. So of course, like, can someone unmute the thing and tell me why is it a topology? You just have to check all the three properties. It will be better if you like interact and all because you'll understand more. I'll help you if you even if you can't do. Fine, I'll only explain. Discrete topology, right? X and power set of X is the topology. If power set of X is the topology, then of course phi and X will be in T. And you take any sets, union of sets will also be a set in X, like a subset of X. And when the topology is a power set, of course it will belong to the topology. Same thing with intersection. So this is also a topology. And fourth one is more interesting than these three. That is called finite complement. Find finite complement topology. So here set is X again, and T is all those subsets such that X minus T is finite union phi. We need to add phi just so that we can satisfy the properties and all. If X is this thing, not a finite space, then you can see like phi won't satisfy the condition U such that X minus phi is finite. So that is why we need to add the thing. And this you take it as exercise to check. Can I proceed now?
Yes.
Fine, thank you. Now,
Could you please show example 4 once more?
finite complement. Feel free to ask questions.
Thank you.
Hmm. So right now what we have done is we have taken a set X and defined some properties, and any subcollection of subsets and all which satisfies these three properties is called a topology, and X comma T is called a topological space. And now we'll study and explore some properties of this space. First, some basic definitions. Open set. Any element of T is called open. Like if a set is called open if it is an element of T. Second definition will be closed set. Closed sets are basically. Can someone guess what will be a closed set?
Complement of the open set.
Yes. So sets whose complement belongs to T. Fine. So can someone tell me what are this thing? What are the closed sets in discrete topology?
X and phi both are closed.
Yes, both are closed and both are open. And what are the open? What are the closed sets in discrete topology?
Again, all subsets will be closed
Yes,
and
yes. So now, starting will just be a this thing, just some collection of definition and all. Now next will be limit point. This will be of a set. I should call it subset because it is in X. So now, see, when I say point, point refers to like a point in X. It is not a point in tau, like not a point in T. So any element of X is called a point. And the thing is called a limit point when you take any open set in which this X is contained. It's this thing. 1 second. Yes, so fine. You take any set. First, I'll define one more thing. Like suppose an open set contains a point X. This open set is called a neighborhood of X. Fine. Now, yes. A point X is called a limit point of a set A if you take if you take any neighborhood of the point X, it's this thing. Deleted neighborhood. Like deleted neighborhood is you remove this point X from its neighborhood. So basically, suppose U is the neighborhood, it is an open set, you remove the point X. So U minus X intersection A is equal to 5. I'll write this down. Like, so this thing, limit point. Fine. This U minus X is called deleted neighborhood. U is a neighborhood, and if you delete X from the thing, it is called deleted neighborhood. Can I proceed? Fine. So next thing will be a limit. Limit, you guys have seen and opened this thing metric spaces, right? What was limit there? Can someone unmute and explain? Define what is the limit of a sequence.
Limit of the sequence xn is x if for all epsilon greater than 0 there exists n greater than 0 such that after all n distance between xn and x is less than epsilon.
Yes, fine. So now you turn this thing into the language of open sets. Fine. A point is called a limit of a sequence if for all neighborhoods of that point there exists an n for such that for all n greater than n the sequence lies inside the neighborhood. Exactly the same thing. No difference. By the way, this is the notation for sequence. instead of writing for all open sets containing x and all, I'll write for all neighborhood of x, for all neighborhoods of x. Let me write it as n naught. Okay, fine. Now this n naught depends on the this thing neighborhood. This n naught is not for all neighborhood. For each neighborhood, you will get an n naught. It's called a limit point if for each open U system there is n naught star x n belongs to U for all n greater than equal to n naught. Fine. Can I proceed now? This is your normal definition, like the same as matrix versus.
Yes.
Fine. Now let me give you a recap because it might be too much definition in the start. Even I won't take it. Somebody
Hello.
teaches so many definitions. So X
I have a
is a
question.
set and T is a collection of subsets of X. T is called a topology if it satisfies these three conditions, like arbitrary union and close under finite intersection. Finite intersection. This is equal to singleton zero, which is not so.
Hello.
Matrix
Am I audible?
is X. 1 second. You can just unmute yourself and ask me. You don't have to raise your hand and all.
Hello. Am I audible?
Are you trying to say something? Like, are you trying to say something? 1 second. Fine, fine. I don't know.
Yeah. Am I audible?
Yes, yes, you're audible right now.
Yeah. Yeah. So I had a question that for the definition of the limit of a sequence and for a set, limit point for a
Hmm.
set and for a sequence. For
Yeah.
sets, we consider a deleted neighborhood of x. So
Hmm.
for in the case of sequence, do we consider deleted neighborhoods? So like we take
No, no, no.
u.
See, yes, I understood your question, and it's actually a nice question only. This was going to be my next point. Limit and limit point is not the same thing. Fine, like a sequence, if you consider them as a set, okay, then that thing also kind of a sequence when you write the sets. Like suppose this is xn, right? You write x1, x2, dot. This is also a set, right? So there's a limit point of this set, or a limit point, a limit of the things and all. These are you need some specific conditions. Okay, like I'll give you an example. This thing one constant sequence one. What is the limit of this sequence?
One.
Yes. So the limit will be 1. Fine. Now consider, like, see the definition of limit point. Now check, is 1 a limit point of the thing? Here the set will be like just the constant one thing, like only the singleton one. So if you delete the thing, then of course any neighborhood wouldn't contain that thing, right?
Yes, there would be no limit.
Yes. So that is the thing. There's a difference. And they're equal, I think, in metric spaces, I think they're equal. I'm not very sure. There's some, I think, condition like there should be infinitely many distinct terms in the sequence and all. That you take it as an exercise or homework to read on your own. But these two are not the same things. That is why the definition is different. But these coincide when there's some specific condition. I think that was infinitely many distinct terms in the sequence.
Okay,
Could
got it.
I answer? What? Fine, thank you. Now the next thing will be subspace topology. Subspace topology. Now, see, this is, suppose Y is a subset of X. You have some topology here, right? You have some open sets here and all. So this will be a very natural question. Like if Y is a subset of X, then if you want to describe a topology on Y, what should it be and all? So this is answered by this thing. Suppose U such that U is open in X, and this is basically T only. So the topology in Y will be U intersection Y. For all U open in X. I don't need to write for all now. Fine. This is the topology Ty. I'll represent it by Ty. This is a topology in Y. Can someone check, like, can someone verify the first property of the thing? Now you represent X by Y and just check U intersection Y is a topology in Y. Can someone verify the first property?
X and Y, so X intersection Y will be Y because Y is subset of X, and phi
Yes, fine.
intersection Y would be phi.
Yes, so the
Therefore,
first property is verified. Yes, thank you. Now the second thing, arbitrary union of this thing, sets in Y will look like,
no, that is just distribution law, right?
yes, these are all basic properties. So I think you can do it yourself only. Like you write union of U alpha intersection Y as union of U alpha intersection Y. Okay, this doesn't make too much sense if I just say the thing. But I hope you get the thing. This is exercise. Check. Fine. After this thing, now we'll start like actually interesting stuff and all. This was all just definitions, but you need to have a control over the definition and all so that it will be easy for you to understand like the things ahead. Till now will be very basic only, right? Can you guys understand the thing? Yes, thank you. So the next thing will be continuous functions. Can someone this thing tell me the definition of continuity in metric spaces? One is that epsilon delta thing, right? That everybody knows, and there's no point doing that thing here because this is topology and we don't have a notion of distance here. there was, if you remember, there was one more equivalent definition, like
For
f.
every open set, U, F inverse U is open in that domain.
Yes, exactly. That is the definition here for a function to be continuous. By the way, this is the definition. F such that x to y. So f inverse u is open for all u open in y. Then the function is continuous. This is the definition. Okay, fine. Now this will be an exercise, like not exercise. We'll discuss this right now only. Clean. Now we'll just play with the properties and different topologies. X to y. Any continuous function from x to y when I equip x with the indiscrete topology. Fine. The claim is continuous function. I'll just write it properly instead of just being lazy. Continuous function from x to y, x equipped with indiscrete topology is constant. Try to think about this. Take 10-20 seconds. Anybody getting something?
Yes, if there exists at least two points in the image space which
Yes.
are in the range, then F inverse of both of those open sets will be open in X, and only open sets in X are null set and interset. So null set
Yes.
will not be the inverse because we said that it lies in the range. So entire set X gets mapped to one single point.
Fine. Fine. That is the proof. Can you guys complete it on your own? This thing
I have
now.
a question that in the
Hmm.
definition, F inverse U is open in X. Is that
Yes. F inverse u is open in X. Like F inverse. Were you asking this thing only? I could not hear you properly.
I was asking that in the definition?
Fine. Fine. Thank you. F inverse u is basically this thing, a set in X, right? So it will be open in X for all u open in Y. So now, as he said, like if you take 2 points in the image, suppose y1, y2, you know there are points in an image, so there this thing. Pullback is kind of, not kind of, it is actually non-empty only. Now you take this thing, inverse image of the thing and all. So it will be the full set. It has to be the full set because it is a continuous function. That thing has to be open.
But it pulls back open set to open set, right?
Yes, fine.
So
Thank you.
if
Like,
I consider a single point, how is that single point an open set in Y?
yes, fine. Thank you. I should say that y is discrete here. Fine. I'll define one more property later, then we do the same thing there. Now the next thing will be, now there's one more claim. This claim will be, you do the same thing and you give X discrete topology this time, no matter what topology you give to Y. Give any topology to Y. So now my claim is, any function f is continuous. Can you see this thing? Like f is any function from x to y, x has this thing, discrete topology. Then any function x is continuous. Any function f is continuous.
Yeah, because F inverse Q will be a subset of X, and anyway, this is an open set.
Yes, that is exactly that is the reason. Like any, you take any this thing, any inverse image, it is an open set only. So always it is open because of discrete topology. So any function is continuous. Now a function is called homeomorphism. Again a definition. You must have heard about all these things, homeomorphism.
No, this is new.
Yes, homeomorphism is a continuous function from x to y. Continuous function from x to y such that f is bijective. Now, as f is bijective, inverse exists, okay? We want the inverse also to be continuous. Suppose there is a function which is continuous, it is bijective, and if inverse is also continuous, that function is called a homeomorphism. And the spaces between which the function is there, x to y, these spaces x and y, they are called homeomorphic. I think you represent it by this homeomorphic. And, and now let us think of an example of homeomorphism. Hmm. Can you guys see this thing? 0, 1.
Just one question.
Excuse me.
What? One question?
Question is that if f is bijective and f is continuous, doesn't that imply that f inverse is also continuous?
No, this doesn't imply the thing. Now, see, or topology, the most difficult thing is giving examples. Like everything is abstract, right? I'll have to think too much and all. Let me think of something. Anything which
You
is
can take interval 0, 1 and S1, I think.
interval 0, 1. I think that will work. Should work.
Are you sharing a screen?
What? Are you?
Are you sharing a screen? At least on my screen, it's not visible.
Yes, I'm scared. I'm sharing my
It
screen.
is visible.
Visible to us.
Oh, sorry.
Fine. Yes. So you can take this thing. If x to x, take the identity function only. This is discrete and this is indiscrete. This works, right? Okay, this function is continuous and yes, inverse is not continuous, it's bijective also. Fine, thank you.
Uh, just a request, can you please repeat the claim one about the indiscrete, about the continuous function in indiscrete topology?
About the continuous function in
Indiscrete
this thing
topology.
or
What was the claim? Uh,
fine. Okay, I did not state it properly. A continuous function from x to y, where x has indiscrete topology and y has discrete topology, is constant.
okay. Thank you.
Uh, yes, so this is a, I should write an example of function which is continuous and is a bijection, but is not a homomorph. Homeomorphism actually like is one of the basic things in topology. Everything will be done using this only. Like this is a very important question. Like are two spaces homeomorphic and all? And to answer these questions, you develop tools that will be very different. Yeah, I think yes. You make some tools and all just to answer this question. This is not very easy to answer. Are two spaces homeomorphic? So now the next thing which I'll define will be basis. Now when I say the term basis, what do you guys think? Like what can be the definition? Like you can't guess the definition, of course it is a bit technical. But what will be the objective of this thing? Basis.
So generating the whole topology with a particular set.
Can you repeat yourself?
It's like the basis in the vector space. Like I'm given a set, particular set, and I'm generating the whole topology from it. Is it?
Kind of like on that line only, but you have to kind of yes make some definition and all. Like you have some technical properties also. Not exactly like vector space, but idea is the same. You just have to generate the whole thing. That is the idea. So basis first. Should I take it last one? No, fine. Definition of a basis is first point. Take any x belongs to x. Okay. I'll define B. B is the collection. Base is a collection of subsets of X. So this script B is called basis. If you take any X belongs to X, there exists a BX belongs to B such that X belongs to BX. This is a very intuitive this thing, right? Property. Like for all X at least you need one set in which the thing is contained. Otherwise, how can it generate the whole thing? Now the next thing is a bit this thing technical. If you take any two basis elements, b1 b2 suppose, and non-empty intersection, there will be a third basis element. There exists of b3 such that x belongs to b3 and this is contained in b1 intersection b2. This is the second property of being a basis. This is the definition. Now we'll come back to this thing, metric spaces. Usual topology in R2. What do you think is the basis there?
Is B3 a strict subset? Like, is that strictness necessary, or is it less?
Am I audible? Make it the Wi-Fi works now.
Yes, you are audible.
Yeah, you're right.
Hello, hello.
I think there is some internet issues on the Vedanta side. He's coming back in a few minutes.
Yeah, it's okay.
Can
I also connect.
can you hear?
Your voice is breaking.
Can you guys hear me right now?
Yes, now it's clear.
Hello?
Yeah, you're audible.
Yes, Wi-Fi is suddenly, I don't know why it stopped working. I think people who are in the hostels must be facing the same thing right now. Can you guys hear me?
Yeah, we can hear you. No issues. Continue.
Fine. Fine. So where was I? People who are staying in the hostels, like, is their Wi-Fi working or something? Can somebody tell me? I think we should wait for 1 or 2 minutes because there was some fluctuation suddenly. I don't know. Saurav, are you there? Or Rahul?
Yes, yes, we are there. We are.
Fine. Fine. So again, I'll this thing repeat the definition of a basis. The first one is very intuitive, right? Like for any point x in x, there should be a element in the basis which should contain the thing. The second one is this thing like if you have any non-empty intersection of two basis elements and there's a point x in it, there should be one more element in the basis so that it is contained in the thing. Fine. Where was I? Yes, I finished around here only. Now this I defined just for explaining you guys product topology. Like I don't know any other way to explain you without telling your basis. Product topology. Is my screen visible?
Yes, it is.
Yes, yes.
Yes, fine. Tell me whenever you can't hear me for like more than 30 seconds or something. Because the Wi-Fi is not very good right now. So now the next thing is product topology. You have two spaces x and y. So now you want to construct a product, right? Like you want to construct new topological spaces from already existing things. So the first thing you do is always like is product and all Cartesian product. So here the underlying space you will take is Cartesian product of the two things. And I'll tell you, fine, like I should tell one more thing before I say this thing. Now, suppose I basis, there's one more reason to define a basis. Topology has too many sets, right? Sometimes it can be, suppose I give you a set X, it is very difficult to tell all the open sets in the thing. So that is where basis helps us. Like I can just give you a basis of a topology, and this is this thing. Like the topology generated by the basis is where like a set is open in that topology if it is the union of some basis elements. So if I give you the topology or I give you the basis, both are the same things, but basis has much less information. So if I give you less information, you get the same amount of information. That is why basis is helpful. For example, in R2 normal Euclidean thing, there are many open sets. Like you can take a countable union of, suppose you take countable union of any open sets, fine. So that is also open. Now you cannot write all the things instead of that thing, I just tell you one more, like I'll follow one more way. I'll just give you the basis. The basis will be all the open balls. This is a very easy way of giving you this thing, defining the topology. Now you know, like any open set, it will just be a union of those elements. So I give you the same information, but with less bookkeeping and all. Like you just need to know all the basis elements are just balls, and you can make unions however much you want. But giving you all the open sets is a very difficult task. There can be too many open sets. That is why base is helpful. Now, yes, base is helpful. This sort of thing, and then product topology. So this thing is defined on the Cartesian product of the two spaces x and y, and you call. I'll give you the basis of the thing, basis of the topology. Basis will be u cross v such that can anyone make a guess what should be the basis?
U is in tau x, V is in tau y, and
Yes, exactly that thing only. U is open in x and V is open in y.
But this did not be a topology, right?
This is a topology also. See, but this thing. Is it a topology? I
for
think
all
it's
x in U there is a Bx, and for all y in V in there is a By, such that Bx cross By is a subset of U plus V.
yes, but now think about this thing. Like, there's one more thing. X is a subset of Tx, Y is a subset of Ty. So X cross Y belongs to this thing, script B. And of course, like every element is contained in X cross Y. So you don't have to take Bx and all these things. That is also right, but this is much easier. Tx, Ty. Fine. This is a topology. Fine. Like,
The thing you explained earlier, I had a question that each set in the topology is a union of basis elements, or is it
yes,
some union and intersection or something like that?
union of basis elements.
Okay, thank you.
Yes. So now, fine. This is the basis only. This won't be the whole topology, I think, because you can take this thing. Uh, Fine. Take R2. Fine. This is the whole space. Delete this point. Delete the point R2 like this. What kind of a set is this?
Open set.
Yes, this is an open set. This thing, U cross V, where both are open. Let me think. U is open in R and V is open in this thing. R again. That is why this B will be a basis. It won't be the topology. Just replace X and Y both by R. So you will get R cross R. Can someone explain me why this can't be written as U cross V? Or what do you think? Like, can it be written or can't it be written?
It cannot be written.
Can you show the definition once again?
Can you hear me?
Yes, yes.
Yes. So this cannot be written as u into v. Like suppose some slice here, you consider the thing somewhere here. This shows 0 should be in the set, right? In u, because u cross v you take. So 0 should be here in, sorry, u or v. Yes, this will say 0 should be in v. And any other point on this thing, y-axis, this will tell you 0 should be in u. So 0 comma 0 should be in this thing, the topology, when if you could write the thing as u cross v. Should I explain it again? Can you guys hear me?
Yes.
Fine. So I'll proceed. The next thing will be compactness. Compactness, the definition is every open cover has a finite subcover. Now, what exactly is open cover? Fine, if I should write it properly. Set X is said to be compact if every open cover has a now open cover is what? Open cover is a collection of open sets in which the set X is there, like contained. Basically a collection of open sets covering X. Then what will be subcover? Subcover is just a sub collection of those sets which also covers the thing. So what compactness is like the next best thing to finiteness. Compactness is saying like a set is compact if I take any open cover of the set. I can always find a finite subcover. Basically, finite number of sets from that collection only which cover X again. Can you guys follow the thing? Like what exactly is the definition?
Yes.
Yes.
Fine, thank you. So a set X is compact if every open cover has a finite subcover. Now let us try to prove this thing. Any okay, fine. First, let me tell you this thing. A subset A of X is said to be compact if every open cover has a finite subcover in like the fine. If every open cover, any collection of open sets which covers A has a finite subcover. Now this open should be in Like you can take the full space also or the normal subspace topology also, doesn't matter. Both will be the same. Subset X is said to be subset is said to be compact if every open cover has a finite subcover. Compactness is a very important thing. Like right, in metric spaces and all, if a space is compact, then a continuous function attains its maximum and minimum on the thing on the set. Now this is
What is the difference in the definitions? Can you please explain?
a difference in definition of what?
The last two definitions, how are they different? Like, isn't it? Uh, so in the
There's
first,
no difference. Like they're same on top one is for the whole
okay,
set.
okay.
Open set in the subspace topology or the thing set X. Fine. Can I proceed now?
Yes, yes.
Yes.
Hello. No audible.
Yes, yes.
Hello. Can you guys hear me?
I can hear you.
Hello.
Yes, you are audible.
Hello. Can you hear me? Yes.
Yes.
Let me share the screen again. Are you guys facing any Wi-Fi problem? Was it my room only? Uh, Fine. Can you see the screen?
Yes, it's visible.
Fine, thank you. Please be a bit more responsive because I won't know. Like, am I teaching to someone or no? Fine. So now, any closed subspace, any closed, I should write subset of a compact can someone unmute and try to like think whatever, like just say whatever you think should be the way to do the thing.
So consider A to be a closed subset of X.
Hmm.
X is compact.
Fine,
So as A is closed, then X minus A is open.
fine,
So consider X minus A union any open cover of X.
yes,
That open cover of X has a finite subcover because X is
yes,
compact. So
fine,
take that finite subcover union X minus A, and that will be a finite subcover of the closed set.
yes. Like in the last thing you really need X minus A, you can just remove the thing because you are covering A. Otherwise, like it was fine. There's a Should I leave it as a exercise or anybody wants me to show the thing? I don't mind showing the thing. Fine. Some people might be shy, so I'll explain the thing. A x minus a. As A is closed, x minus a is open. Fine. Now you take any cover of A, any open cover of A. Suppose I take some. 1 second. Yes. A is contained in this open cover. Fine. You take union of U alpha union x minus a. Exercise. This is an open cover of X. Can everybody see this thing? Like if union of U alpha is an open cover of A, then union of U alpha and with this thing X minus A will be an open cover of X.
Yes.
Fine now. Yes, now as X is compact, now you're using compactness of X. There exists finitely many sets which cover X. Suppose U12, without loss of generality, I can call them U12 UR. Now this UR, fine. There are two cases. Like X minus A can be one of them or it might not be one of them. Suppose it is one of them. If X minus A is one of them, suppose the last one is equal to X minus A. Just remove that thing and U12 UR minus 1. This will be a finite open cover of A. You get the thing, right? X minus A is kind of useless for covering A. Is the complement. So you can just discard the thing. And if X minus A is not there, then you need all U1 to UR. Case 1, case 2. X minus A doesn't belong to UI. Belongs to These are the two cases. Is there anyone who wants me to repeat the thing? Like some part is not clear. All these things are very important. Like that is why I asked. This will be used in every course. Most of them. Like I can't say every. Every is a very strong condition.
Yes, it's fine.
So yes, fine. Next exercise. Any continuous uh, compact subset. Now, can someone answer this thing? Basically, the thing which this thing is saying is like image of a compact subset under a continuous map is compact. See, in topology, everything you have to do from basic definitions only. You don't have any tools. Just see what is continuous, what is compact, and then once you start writing, you will be able to kind of get on the this thing right track. Like, what do you have to do? You have to think like this. Like you have to show. Suppose I take x2y. Now I can replace y by f of x. Continuous. Fine. Point. Like if I replace y by f of x, then also the function remains continuous. So I assume f is from. Can you guys hear me?
Yes, we can hear.
Fine.
Yes.
Fine. Anyone who wants to try how to do the thing? See, the idea is this thing. You just have to take any open cover in the image. You just look at the, and you
We
just
take
want to
an
find a finite subcover. What?
Yeah, we take an open cover of fx,
Yes.
and since f is continuous, so f inverse u is open in x.
Yes. Fine.
So f inverse u alphas will basically be open cover of x, and then by using compactness of x will be true.
Yes. Fine. That is the idea. So all these things are not very difficult if you're clear with the definitions. Like when I say open cover, all the sets have to be open. And now, if I give you an open set, then the pullback of the open set is open only. And then you form a cover of the space X, and X is compact. So there will be a finite subcover of the sets. And now see the image of these things. They'll cover Fx, and that will be a finite cover. That is the idea. I hope you guys can complete the proof now. Anybody who wants me to explain the thing again? Fine, like this is like the basic of compactness, product topology, bases and all. Fine. Now I'll tell you just one more important thing. This will be used for cost of space. Have you guys heard of this thing? Cost of space. This will be used in many courses.
Yes.
Cost of space is basically you can separate any 2 points. Suppose I give you any 2 points. You can find open sets so that the intersection is non-empty. Basically, it is used to separate points. Fine, like If I make it like in picture, then or something, fine. You take any 2 points and then you can separate them by open sets. And now this is an exercise. Think about this thing. It is if the space is Hausdorff, if the space is Hausdorff and
So can you repeat the definition of Hausdorff space?
Hausdorff, fine. Should I write it down? Hausdorff space is given. Take any two take any 2 points x and y. No, sorry. By the way, this was the notation which was I was following. Very late to tell you now. X is the space. X will be the topological space and T is the topology. So take any points x and y belonging to x. You can find open sets u and v such that x belongs to u, y belongs to v, and u intersection v is equal to phi. This is the definition. Take any 2 points, you'll find two open sets such that like both points are contained in one of them. A open set containing one point and another open set containing the other point, and the intersection is this thing, empty. Is it fine?
Yes, yes.
Yes. Like it might be very heavy to digest because all these definitions are given over this thing. It takes one topology course to give all the definitions and all, and I kind of told you everything in one talk. So I don't expect you guys to remember everything, but now you can forget the previous things. Okay, Hausdorff thing is now new. If the space is Hausdorff and Xn is a sequence, prove this thing. And Xn is a sequence, then the limit of the sequence can somebody think of a solution? Again, you have to use the basic definitions only. What exactly is limit? Limit was what? Like a point x is called a limit of a sequence if for all neighborhoods of x there exists n. So
Okay,
that after.
so assume that for the sake of contradiction, assume that xn converges to x and xn converges to y.
Fine.
By Hausdorffness, we can find a ball such that there's a ball around x and there's a ball around y, which does not contain any point. However, for since xn converges to x, there exists n1 such that for all n greater than equal to n1, xn's will be inside the ball. Inside that epsilon ball containing x. Similarly, for y, they will find such n2. Then take the maximum of n equal to maximum of n1 and n2. Hello.
Yes, it's correct, I think. Except for balls, I think it will be open sets.
Yeah, I mean that's what I meant. That's what I mean. Hello.
I think there are again internet issues.
Can you repeat the thing? My Wi-Fi went again.
Sorry, yeah. So I was saying that we can find some open set around x and open set around y, such that their
Yes.
intersection is null. However, since
Fine.
xn converges to x, for there exists n1 such that uh, for all n greater than equal to n1, xn is in the open set around x.
Fine.
And similarly, before we can find n2 for the y. Now take the maximum of n1 and n2.
Yes.
And then for all n in that maximum, it will it will belong into both the sets. So it will belong in the intersection, but then we have a contradiction because the intersection is 5.
Yes, correct. That is the idea. Like not the idea, that is the proof. Everybody got the thing? Like, can someone explain the thing again?
Yeah, it's fine now.
It's fine. Fine.
Yes, yes.
Do you want? Yes, fine. So this is basically the what I wanted to cover today. Do you guys feel like knowing one more thing? Like, I don't know. I can tell if you want to know what is connectedness and all. Otherwise, I'll stop today. Like, I'll stop now only. Fine. That is it. Thank you.
Thank you.